Hi friend, welcome all to my educational channel Math A to Z. This class basically for higher level competitive mathematics exam, and it is also useful to the graduate level mathematics student also. And in this class we discuss some important MCQ type question from the part linear programming problem. The first question is, for the LPP mean Z equal to 7x1 plus 8x2 plus 3x3 subject to 2x1 plus x2 plus 3x3 equal to 7, x1 minus x2 plus 4x3 equal to 3, with x1, x2, x3 greater equal to 0. The solution x1 equal to 1, x2 equal to 2 and x3 equal to 1 is option 1 feasible but not basic, option 2 basic but not feasible, 3 feasible as well as basic, 4 neither feasible nor basic. Now the answer is clearly this solution x1 equal to 1, x2 equal to 2 and x3 equal to 1 satisfy these two equations, because here 2 into 1 plus 2 plus 3 into 1, that is 3, 4, 3 to 5 to 7, okay, and this is 1 minus 2 plus 4, that is 1 minus 2 plus 4, that is 3. That is, this solution satisfies this and this. Here number of equation is 2 and number of variable clearly 1, 2, 3. So any basic solution must contain 3 minus 2, that is 1, must contain 1 0, but here this solution does not contain any 0. So this is the feasible solution because all of xj greater equal to 0, but this is not basic. So the option A, that is, or option 1, that is feasible but not basic, is correct. And option 2 is not correct because here given that basic but not feasible, but clearly this solution is feasible. And option 3 feasible as well as basic, but we here see that it is not feasible and it must be feasible, not basic, so the last option B also wrong. The question is, for the system x1 plus 2x2 plus x3 equal to 3, 2x1 plus x2 plus 5x3 equal to 9, the solution x1 equal to 5, x2 equal to minus 1, x3 equal to 0 is option 1 basic and feasible, 2 not basic but feasible, 3 basic degenerate, and the last option is basic non-degenerate. Here it is given that x3 equal to 0 and here the number of equation is 2 and the number of variable is 3. So for the basic solution 3 minus 2, that is one variable must be 0, and here it is given that x3 equal to 0. Now two non-basic variable, that is x1 equal to 5 and x2 equal to minus 1, and the column vector corresponding to x1 and x2 is 1, 2, 2, 1. And the determinant is equal to minus 3, that is not equal to 0. So this must be a basic solution. Basic. But this is not feasible because this is less than 0. And x1 and x2 are two non-basic variables, and two non-basic variables are also non-zero. Okay, and one, this is basic variable, this is 0. So this is basic and non-degenerate. Non-degenerate. Okay, so the option 4 is correct. Next question. Which of the following is not a convex set? Option 1. Set x1, x2 such that x1 square plus x2 square less equal to 3 and x1 square plus x2 square greater equal to 1. Option 2. x1, x2 such that 9x1 square plus 4x2 square less equal to 36. Option 3. x1, x2 such that x1 less equal to 5, x2 greater equal to 3. And the last option x1, x2 such that x1 plus 2x2 less equal to 5. If we draw the geometrical figure for each set, then for the first set we get, this is x1 axis, this is x2 axis, and this is a circle with center, origin and radius root 3 unit. That is this type of circle, and the region is inside, and this circle is x1 square plus x2 square greater equal to 1. That is, this circle is of radius 1 and center exact 0, 0. And the region is outside the circle. So the common region is clearly the shaded region. We shaded this region. Okay. And it is easy to see that this set is not a convex set, because if we take here a point and here a point, then this line segment does not wholly belongs to the set. So this is not convex. So our question is, which set is not convex? So the option 1 is correct. If we consider option 2, then it is an ellipse, and ellipse is of the form this. Okay, so and the region is inside. So clearly this is a convex set. If we take the third set, then this is x1, this is x2, and x1 less equal to 5. This, the region is along the origin, and x2 greater equal to 3, that is this, and the region opposite to the origin. So the common region is this, and clearly this set is also convex. And the last set is as, here this is a straight line with 5, 0 and 0, 5 by 2, and this straight line, and the region is along the origin. So this is the region. So it is also convex set. So here only one set which is not convex is the first. Hyperplane is a convex set with one extreme point. Option 2, finite number of extreme points. Option 3, infinite number of extreme point, and the last option is no extreme point. We know that the hyperplane is of the form Cx equal to z. This is the objective function of LPP, and this is also called the hyperplane for the particular value of z. Now, if we consider the hyperplane in 3 dimensions, then we get the hyperplane as ax plus by plus ax1 by1 bx2 and cx3 is equal to z, and the for particular value of z, that is d. And this is a plane in 3 dimensions, and we know that for a plane have no extreme point, similar as a straight line have no extreme point. So we say that a hyperplane have no extreme point. Okay, so the option 4 is correct. Last question of this class is the LPP max z equal to minus 3x1 plus x2 subject to 2x1 plus x2 less equal to 4, minus x1 plus x2 less equal to 1, x1 plus x2 greater equal to 1, minus 3x1 plus x2 greater equal to minus 3 with x1 x2 greater equal to 0 has 1. Unique optimal solution, 2. Alternative optimal solution, 3. Infeasible region, and 4. Unbounded region. We draw all the straight line and indicate the feasible region as this is x1 axis, this is x2 axis. The first straight line is x1 2 unit 2 0, and in the side x2 this is 4 unit 0 4, and the straight line is like this, and the region along the origin. This is the first straight line. Second is this is minus 1 0, and this is 0 1. So this, and this is the line 2 and the region along the origin, and the third line is like this. This is 0 1 and 1 0, and if we find the intersection of first and second, then we get the intersection as 1 2, and the last line is x1 by 1 and x2 by minus 3, x1 by 1 and x2 by minus 3, that is this, and minus 3 this type of straight line, and this is the last straight line. This is 4, and the region is inside. Okay, so the common region is this shaded region. This is the feasible region, and we find the intersection of first and fourth equation, and we get the point as 7 by 5 and 6 by 5. Now we get a closed feasible region with vertex, 4 vertex, 1 0, 7 by 5, 6 by 5, 1 1 2 and 0 1. So we now check in which vertex the objective function is maximum. For the vertex 1 0, we get this is minus 3. For the vertex 7 by 5, 6 by 5, this is also minus 3 into 7 by 5 plus 6 by 5, that is 21 plus 6 by 5, that is minus 3 also. at the vertex 1, 2, this is minus 3 plus 2, that is minus 1. And at the vertex 0, 1, this is 0, 1, this is 1. So we get 4 value at the 4 vertex. And we see that here and here we get the minimum value. Okay, we get the minimum value here minus 3 and here minus 3. Sorry, this is mean, maybe mean. Okay, so the optimal solution occurs at 2 vertex, 1, 0 and this 7, 5, 5, 6 by 5. So we get infinite number of optimal solution. All the point in the line segment joining these 2 points are the solution of this problem, are the optimal solution of this problem. So we get infinite number of optimal solution. And here the option is alternative optimal solution, that is more than one optimal solution. So the option 2 is correct, and this is alternative optimal solution.